right, welcome to Unit 5, Lesson 6, homework help. This one's called All for One and One for All. So let's get started. Despite the title, All for One and One for All, we are not starting with 1, we're actually going to start with 2. So let's scroll down just a bit and zoom in, and we'll start with number 2. So this first question, for the readies, it says find the value of each square root. So remembering that a square root is like a question. A square root is asking what number must be squared in order to get the number that is large and inside, right? So it's saying like what number squared equals 69, right? What squared equals 169? Sorry about that. And the question on this first one, right? We might know that like 10 times 10 is 100. 11 times 11 is 121, 12 times 12 is 144, and 13 times 13, right, they keep getting bigger. 13 times 13 is 169. So the square root of 169 is just 13, right? 13 because, right, 13 times 13 equals 169, right? So that's like our check is that 13 squared, right? This is the same as saying 13 squared equals 169, right? So that's our check. So for number 2, we have 13. Oh, and we actually were just saying the square root of 100, well, that's asking what times itself is 100. And we already know that that is 10, right? 10 times 10 is 100. So we'll write that. 10 times, 10 times 10, there we go, equals 100, which means 10 squared equals 100. So the square root of 100 is 10. And the same goes for number 6, right? It's good to know your perfect squares on the way up. So like 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and so on. And if you get all the way to 9, right? 9 times 9 equals 81. Oh, that's just the 1 though. Right, 9 times 9 is 81. Right, so 9 squared equals 81, which means that the square root of 81 is 9. There we go. All right, let's move on. Solve for x. 3 to the x equals 81. So that means 3 times itself some number of times. So 3 times 3 times 3, and so on, right? So how many 3's would we have to multiply by themselves, right? 3 times 3 times 3. So like how many of these 3's would we have to multiply by itself? Well, 3 times 3, right? This part would just be 9. This part would be 27, right? And then if we include this part, oh, I didn't go far enough, did I? Right? This last part, right? 27 times 3, if we include that, that's going to be 81. So we're looking at this many 3's, which is 4, right? 4 3's, which means 3 to the 4th is 81. So we're solving for x, so x equals 4. All right. Let's move on to the next question. We've got 2 to the x equals 32. We'll do this one in purple. So 2 to the x equals 32. Well, 2 to the first, remember, if we go back all the way to sequences, this is just a geometric sequence of sorts, right? We're multiplying by 2 each time. So if we have our x in this column, and then our output in the other column, right, our output. Oh, wasn't trying to do that. Hang on, delete that. Our output, which is going to be not 0, right? If our x is there and our 2 to the x is here, right, what we're going to have is if x is 1, then 2 to the x is just 2, right? If x is 2, then we have 2 to the x is 4, right? 3 would go to 8. 4 would go to 16, right? And 5, that is a 5, right? 5 would go to 32. So what x do we need in order to reach 32? If 2 to the x needs to be 32, then x must be 5. So in this one, x equals 5. All right, for number 10, do we recognize this 144 as a perfect square? This is saying x squared equals 144. Well, that sort of means we need to take the square root of both sides, or it's asking what times itself. Sorry, this shouldn't have been done in purple, right? It should be in green for this question. What times itself is equal to 144? Well, we could make another table, right? We could make a table and start out with just, like if we have x here and x squared over here, right? We could always do, right, 1 squared is 1, 2 squared is, not 3. Not 3, it's 4. 2 squared is 4, right? We could always do 2 squared is 4, 3 squared is 9, and so on. But how high would we have to go until that right column becomes 144? Well, we might be able to skip ahead, right? Maybe we skip ahead and we know that 10 squared is 100. So maybe we just try, right, 11 and 12 and so on, right? 11 goes to 121, 12 goes to 144, right? So that's what we're looking for. So x in this case, if x squared is 144, then x is 12. And we'll go back to purple for this last one. X cubed is 125. Now we could make a table again, right, where we have x and then x cubed. We could do that. Do you want to try that? We'll try that as our solution, the way to find a solution here. So we'll make a table again. We'll have x in this column, and then x cubed, or x times x times x, in the column next to it. It's going to be a little bit trickier, but if we have, right, 1, then 1 times 1 times 1 is still 1. Right? If we put a 2 in, then we get 2 times 2 times 2, or 2 times 2 is 4, so 4, and then 4 times 2 is 8. If we plug in a 3, right, 3 times 3 is 9, 9 times 3 is 27. All right, we're getting up there, right? 4 times 4 is 16, 16 times 4 is 64. Oh, that was a big jump. I have a feeling it's going to be 5, but let's check. 5 times 5 is 25, and then 25 times 5, well, if we have like 5 quarters, how much money do we have? Well, 4 quarters is dollars, so that'd be 100, and then one more would be 125, right? $1.25 or 125 cents. So 5 cubed, or 5 to the third, is 125. So we have x equals 5, because 5 to the third is 125. Right? So that is our solution to number 11. Now we're looking at the set. All right, constraints A, B, and C are graphed as shown. Constraint A is blue. Yep, I see that. It's on the left and it looks tall and skinny. Constraint B is green. That one's sort of short and wide. And constraint C is purple. Okay, I see. Constraint C is sort of this, actually looks fairly equally high as it is, or tall as it is wide. So that looks, and it looks to be the bottom sort of left of the figure. So let's see. Indicate where on the grid each of the following might exist by labeling it. Oh, so we're just labeling here. All right, so we're going to use a bunch of different colors here. Let's see. Where can coordinate pairs that satisfy only A and B be found? All right, so we're only looking for A and B, but not C, right? Only A and B. So if A is the blue and B is the green, we need the blue and green overlap, but not purple overlap. So it looks like we're going to pick a new color for this. We'll pick green and blue. We'll go with this sort of lime green looking thing. All right, so we'll do this portion in lime green, and it looks like that's going to be just this section here. gonna work. Oh, just that section there. All right, that's where A and B, but not C, can be found. All right. Part B, where can coordinate pairs that satisfy only B and C be found? So now we're looking for B and C, but not A. So A is the blue, so not looking anywhere there. So we're only looking for the overlap between green and purple. All right, green and purple. Let's switch this color. We'll go with this green and purple. Let's go with this like sort of reddish pink. So we'll label it. We're going to do it in reddish pink. And B and C overlap here, it looks like. Right? It looks like this area right here. Right? That is the portion where B and C overlap, but A does not. Now the question, right, part C, where can coordinate pairs that satisfy only A and C be found? All right, only A and C appears to be, we'll do this in a light blue, I suppose. Let's do this in a light blue. A and C look to overlap here without overlapping B, right? So we'll do this section. Excellent. And then finally, where can coordinate pairs that satisfy all three constraints be found? We'll do this in, what color do we want? How about orange? We'll do orange for this one, for all three of them. That's going to be in this section here, right? Nope. Did it draw? Yes, it did. Okay, there we go. Right? It's going to be in this section here. All right, and that is where all of them overlap. All right, so those are our three. Those are the sort of areas of overlap, right? So we have where A and B happen, but not C, where A and C happen, but not B, where B and C happen, but not A, and then where all three of them happen. So, perfect. Let's move on, see what other questions we have. Write the inequality that represents the shaded region for each graph in slope-intercept form. Write the inequality that represents the shaded region for each graph. Okay. Let's go up high, and it looks like we're just doing 15. Okay. So write the inequality that represents the shaded region. All right, well, to start off, I noticed that the line, right, the line does not have, it's not a solid line, it's a dashed line. So that means to me that it's going to be either, right, is going to be either less than or it's going to be greater than, but there's not equal to, right? Not equal to, right? So it's not going to have equal to as part of it. I also see that it is above. It looks like y, right? The y values, right? It's all the y values that are above the line, right? So if we were looking at, is this like a mountainside, right? It's like if we were looking at a mountain, are we looking at the sky, which is above the mountain, or sort of the rock, which is below the surface of the mountain? So we are looking at the sky here, so that's going to be the greater than. So we're going to start with our y's must be, right? This is the greater than logo up here, right? So y is greater than, but not equal to. And now it's going to fit. Now we have to figure out what is, what's our slope, or what are our intersects? Like, what are we looking at? So it looks like we have our intercept right here, right? Our y-intercept is right there, and that seems to be the point. Let's go with 0. I think it's 0 minus 4. I think that's the point. I think that point is 0 comma minus 4, which means it's going to be something x, right? We don't know our slope, but we know our intercept is at negative 4. And then we're looking for the slope. So it looks like we can go over 2 and up 4, and that looks like another point, right? So if our slope is up 4 over 2, that means our slope is 2, right? So our slope is up 4 over 2, or 4 divided by 2. 4 divided by 2, which is equal to 2. And our intercept is 0 comma negative 4. So we'd write the equation as y is greater than 2x And then our intercept, which is -4, right? And I believe that that is going to be our proper inequality, which describes the shaded portion of the region, right? Or the shaded region on the plane. So that's going to be our inequality there for number 15. And let's see the go portion. For each inequality and graph, shade the half plane that contains the solutions. Okay. So inequality and graph. So we should get inequalities and graphs and then figure out which half plane contains the solution. So let's go look. We were just doing 17 and 18. So let's see 17 first. Let's scroll down so we can see it all. Excellent. All right. Y is greater than or equal to negative 3x plus 5. So I can tell by looking at the line graphed, it's a solid line because we have greater than or equal to, right? This equal to portion, right? This bottom portion, this makes it a solid line. Oh, did not mean to make a new note there. My mistake. Let's delete that. It happens sometimes. So that's what makes it solid. And then y being greater than, let's try to move this a little bit, right? Because y is greater than, that's going to mean we go above the line, right? It's a solid line, and greater than means we go above the line. So we are going to make our shaded region, oh my gosh, we're going to make our shaded region in green, and it's going to be the portion above the line. So we pick any point and we go up from it, and this is going to be our shaded region. So we've got the shaded region. All right. And we've got it filled in pretty well here. Excellent. All right, so that is our shaded region. We should have the sort of top right portion. All right. Now we've got another one. We're going to end up doing this one in purple since we just did the previous one in green. I figure we should switch to purple for this one. And we're going to try a lighter purple. Why not? Let's mix things up. 5x minus 2y is less than or equal to 10. All right, 5x minus 2y is less than or equal to 10. Now, since this isn't in slope-intercept form, it's a little bit trickier to know whether this less than or equal to means above line or below line. But what we do know is that this is what makes the line solid. That makes the line solid. Now, what do we know about, right? We know that points are going to be on the line, and we also know that solutions to this inequality will only be either above the line or below the line, right? And I noticed that the point 0, 0, right, this point right here, right, the origin, is not actually, that's not on the line, which means if we plug this in, we can determine whether that satisfies the inequality or not, right? And that's going to be a super easy way to check. So let's see, if we plug in that 0, 0, right, we'd have, we'll just on the right side, let's do 5 times 0. Here we go, 5 times 0 minus 2 times 0 is less than or equal to 10. All right, is that true? Is 0 minus 0 less than or equal to 10? Well, this is just 0 is less than or equal to 10. And yes, that is true, right? 10 is greater, so 0 is less than 10. So we know that the origin, 0, 0, or that point 0, 0, is in the correct, or is in the shaded half of this plane, which means we can take our fill-in tool, right, our shader, and we can start filling in, right, this top right side. or sorry, not top right, this top left side. Right, so we get there, fill in the whole region, and there we go. All right, so it's going to be that sort of above the line and to the left. So that's good. All right, let's carry on. Now, there are a bunch of ways to have figured that out as well, but I always recommend if you can plug in the 0.00, it makes it so easy to figure out. So that's always my suggestion is try the 0.00 if it's not on the line. But for now, let's move on. Let's see if are we doing number 19? Oh, a little bit of suspense here. A little bit of suspense. No, we're not doing number 19. So that wraps it up for this homework help. I hope it was helpful.